Picture a galaxy, not an abstract concept. An actual galaxy, 100 billion stars, each one a sun, many with planets orbiting them, the whole vast structure held together by gravity, rotating slowly in the dark like an enormous cosmic pinwheel. Now picture that galaxy spinning. The stars on the outer edge of the galaxy are moving. Fast, astonishingly fast, far faster than they should be. Here is why that matters. When you spin a ball on a string and release it, it flies outward. The faster it spins, the stronger the string needs to be to hold it. In a galaxy, gravity is the string. The faster the outer stars move, the more gravity is needed to keep them from flying off into the void. But when astronomers calculated the gravity produced by all the visible matter in a galaxy, all the stars, all the gas, all the dust, everything they could see, they got a number far too small. The outer stars of galaxies are moving so fast that there is not nearly enough visible matter to hold them in. By all rights, they should have flown apart billions of years ago. The galaxies we see, the beautiful spirals, the elegant ellipticals, should not exist. And yet they do. Something is holding them together. Something we cannot see. Something that emits no light, reflects no light, absorbs no light. Something that interacts with normal matter only through gravity. Invisible, undetectable by any telescope ever built, present everywhere in the universe, in quantities that dwarf everything we can observe. We call it dark matter, and it makes up approximately 27% of the total energy content of the universe. Everything you have ever seen, every star, every galaxy, every planet, every atom of ordinary matter in the entire observable universe makes up just 5% of what exists. The other 95% is dark, and we have almost no idea what it is. The story of dark matter begins not with a dramatic discovery, but with a quiet, persistent woman doing extraordinarily careful work that almost nobody wanted to believe. Her name was Vera Rubin. Born in Philadelphia in 1928, Vera Rubin fell in love with astronomy as a child, lying awake at night watching the stars wheel past her bedroom window. She pursued that love through a world that was, to put it mildly, not enthusiastic about women in science. When she applied to Princeton's graduate astronomy program in 1948, she was told that women were not admitted. She went to Cornell instead, then to Georgetown, earning her PhD in 1954. Throughout her career, she faced barriers that would have stopped most people entirely. She did not stop. In the 1960s and 1970s, working at the Carnegie Institution in Washington with her colleague Kent Ford, Rubin began doing something that sounds straightforward, but required extraordinary patience and precision. She measured the rotation speeds of galaxies. Specifically, she measured how fast stars at different distances from the center of a galaxy were moving. The expectation, based on Newton's laws and confirmed by everything astronomers understood about how gravity works, was clear. Stars close to the center of a galaxy, where most of the mass is concentrated, should move fast. Stars far from the center, in the outer reaches where mass is sparse, should move slow. The same way the inner planets of our solar system orbit the Sun faster than the outer ones. Mercury races around in 88 days. Neptune takes 165 years. This prediction is called a Keplerian rotation curve. What Rubin and Ford found was something completely different. The outer stars of galaxies were not slowing down. They were moving at roughly the same speed as the inner stars. The rotation curves were flat, not declining as expected, but flat. This was impossible. By every calculation, every model, every understanding of how gravity and mass worked, the outer stars were moving far too fast. There was nowhere near enough visible mass to produce the gravity needed to keep them in their orbits. Rubin's first reaction was to assume she had made an error. She checked. She rechecked. She measured more galaxies. Dozens of them. Then hundreds. Every single one showed the same thing. Flat rotation curves, outer stars moving too fast. Too much rotational speed for the visible mass. Something was wrong with the physics. Or something was wrong with our picture of what was in the galaxies. Rubin concluded, carefully, conservatively, with the caution of someone who knew her extraordinary claim would require extraordinary evidence, that the galaxies must contain far more mass than was visible, a vast halo of invisible mass surrounding each galaxy, extending far beyond the visible stars, providing the extra gravity needed to keep the outer stars in their orbits. Invisible mass. Dark matter. The response from the scientific community was, initially, skepticism. Rubin was not the first to suggest the idea. Swiss astronomer Fritz Zwicky had proposed something similar in 1933, based on the motions of galaxies within clusters. But Zwicky was known for making bold claims, and his dark matter proposal was largely dismissed. Rubin's evidence was harder to dismiss. It was systematic. It covered hundreds of galaxies. It was meticulously careful. And it pointed to the same conclusion every time. By the 1980s, the scientific community had largely accepted it. The universe contains far more mass than we can see, and we still do not know what it is. Let's put the scale of dark matter in perspective. Everything you have ever seen, every star in the night sky, every planet, every moon, every asteroid, every atom of gas floating in the space between galaxies, is made of ordinary matter. Protons, neutrons, electrons. The stuff that physics has spent a century understanding. The stuff that makes up you, your phone, the air you breathe, the earth beneath your feet, the sun above your head. All of that, everything, accounts for approximately 5% of the total energy content of the universe. Dark matter accounts for approximately 27%. That means for every kilogram of ordinary matter in the universe, every proton, every neutron, every electron, there are roughly 5 times as much dark matter. 5 to 1. The universe is not mostly made of the stuff we understand. It is mostly made of things we don't. Dark matter outnumbers ordinary matter 5 to 1, and dark energy, the mysterious force accelerating, the expansion, makes up the remaining 68%. The universe we can see, touch, measure, and understand makes up less than 1/20th of everything that exists. We are the minority, the exception, the thin, luminous frosting on a vast, invisible cake. And dark matter is not evenly distributed. It is structured. Computer simulations of the universe, run on the most powerful supercomputers available, incorporating the gravitational effects of dark matter, produce a large-scale structure that matches what we observe with extraordinary precision. A cosmic web, vast filaments of dark matter stretching across hundreds of millions of light years, with galaxy clusters at the intersections where filaments meet, vast empty voids in between. The same structure we see when we map the positions of galaxies across the observable universe. The galaxies are not randomly distributed. They trace the dark matter. They form where dark matter is dense, along the filaments, at the nodes. They avoid where dark matter is sparse, in the voids. Dark matter built the cosmic web. And the cosmic web is the skeleton on which every galaxy, every star, every planet, and every living thing in the universe is hung. Without dark matter, there would be no large-scale structure, no filaments, no clusters, no galaxies. Without dark matter, there would be no us. Before we get to what dark matter might be, it is worth spending a moment on what we know it is not. Because one of the most important things science does is rule things out. And in the case of dark matter, ruling things out has proven remarkably difficult, but also remarkably productive. The first obvious suggestion was that dark matter might simply be ordinary matter that we can't see. Dim stars, cold gas clouds, black holes, rogue planets, objects made of protons and neutrons just like everything else, but too faint or too dark to detect with our telescopes. These were called MACHOs, massive astrophysical compact halo objects. A deliberately memorable acronym for a class of candidates that seemed, at first, plausible. Astronomers searched for MACHOs using a technique called gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the star's light, creating a brief, characteristic brightening. By monitoring millions of stars and watching for these brightenings, astronomers could count the MACHOs in our galaxy's halo. They found some, but nowhere near enough. MACHOs exist. There are dim stars and cold objects and black holes in the halo of our galaxy, but they account for only a small fraction of the dark matter, not enough to explain the flat rotation curves, not enough to account for the 5-to-1 ratio. The second candidate was neutrinos, the ghostly particles produced in nuclear reactions that interact so weakly with ordinary matter that trillions of them pass through your body every second without touching a single atom. Neutrinos have mass, very small but non-zero, and they are produced in enormous quantities by stars and by the Big Bang itself. Could the universe be filled with enough neutrinos to account for dark matter? The answer, again, is no. Neutrinos move too fast. They are what physicists call hot dark matter, particles moving at close to the speed of light. Hot dark matter cannot clump together on the scales needed to form galaxy halos. It smooths out rather than clustering. A universe filled with neutrino dark matter would not produce the large-scale structure we observe. The structure we see demands something slower, something that can clump, something cold, cold dark matter, a new class of particle, something that moves slowly compared to the speed of light, something that interacts gravitationally but not, or barely, electromagnetically, something that was present from the very early universe, clustering under gravity to form the seeds of the cosmic web. Something that does not exist in the standard model of particle physics, the extraordinarily successful theory that describes all known particles and forces. Something new. Not everyone is convinced that dark matter is the answer. A significant minority of physicists and astronomers have argued, persistently and with genuine scientific rigor, that the flat rotation curves and the missing mass problem can be explained not by adding invisible matter, but by modifying our understanding of gravity. The leading alternative is called MOND, Modified Newtonian Dynamics, proposed by Israeli physicist Mordechai Milgram in 1983. Milgram noticed something that the dark matter hypothesis doesn't naturally explain. The flat rotation curves of galaxies don't just exist. They follow a precise, tight relationship with the visible matter in the galaxy. The more visible mass a galaxy has, the faster its outer stars rotate. This relationship, called the radial acceleration relation or the Tully-Fisher relation, is extraordinarily tight. Far tighter than you would expect if dark matter were a separate component distributed independently of the visible matter. Milgram proposed that at very low accelerations, the kind experienced by stars in the outer reaches of galaxies, Newton's law of gravity changes slightly. Instead of the force falling off as the inverse square of distance, it falls off more slowly. This modification produces flat rotation curves naturally, without any dark matter at all. MOND works remarkably well for individual galaxies. It predicts rotation curves with impressive accuracy. It explains the Tully-Fisher relation naturally. But it struggles with galaxy clusters. And it has serious difficulty explaining the bullet cluster, the separation of mass from gas in a collision that dark matter handles naturally. More sophisticated versions of MOND, called relativistic MOND or TeVis theories, attempt to address these problems. They have had partial success but have not displaced dark matter as the mainstream view. The debate between dark matter and modified gravity is one of the most interesting ongoing controversies in cosmology. Both sides have serious evidence, both sides have serious problems, and both sides agree on one thing. Something is wrong with our current picture. Either there is matter we cannot see, or gravity works differently than we thought. Either way, the universe is not behaving as the physics we learned in school would predict. Something is missing. One of the most compelling pieces of evidence for dark matter comes not from galaxies or galaxy clusters, but from the very beginning of the universe. The cosmic microwave background. The ancient light released 380,000 years after the Big Bang that we discussed in an earlier video is not perfectly uniform. It is mottled with tiny temperature variations, hot spots and cold spots that represent density fluctuations in the early universe. Regions that were slightly denser than average, regions that were slightly less dense. These fluctuations are the seeds of all the structure in the universe. The dense regions eventually collapsed under gravity to form galaxies. The underdense regions became the vast cosmic voids. The pattern of these fluctuations, their size, their amplitude, their distribution, is exquisitely sensitive to the composition of the universe. How much ordinary matter, how much dark matter, how much dark energy. The relative amounts of each leave distinct. Fingerprints in the CMB. When physicists analyze the CMB in detail, using satellites like WMAP and Planck that have mapped the ancient light with extraordinary precision, they find a pattern that is beautifully consistent with a universe containing approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. The same numbers that rotation curves give us, the same numbers that gravitational lensing gives us, the same numbers that the large-scale structure of the universe gives us. Dark matter is not just an ad hoc fix for one anomalous observation. It is a consistent feature of a universe described by multiple independent lines of evidence, all pointing to the same composition. The CMB fluctuations also tell us something important about the nature of dark matter. The pattern of fluctuations is consistent with cold, dark matter, particles that were moving slowly in the early universe, allowing structures to form on small scales first. Hot, dark matter Fast-moving particles like neutrinos would have smoothed out the small-scale fluctuations, producing a different pattern. The CMB tells us cold, not hot, slow, not fast, and not ordinary matter, not protons and neutrons, because the acoustic oscillations in the CMB are sensitive to the amount of ordinary matter separately from dark matter, and they give us 5%, not 32%. The universe is telling us, in multiple languages, the same thing. There is something out there. It is cold. It is not ordinary. And it is 5 times more common than everything we have ever known. One of the most powerful pieces of evidence for dark matter comes not from observation, but from simulation. Starting in the 1980s and accelerating dramatically with the growth of computing power, cosmologists have built computer simulations of the universe. Beginning with the initial conditions revealed by the cosmic microwave background, a nearly uniform early universe with tiny density fluctuations, they have run the laws of physics forward in time to see what kind of universe those initial conditions produce. The most sophisticated of these simulations, projects like the Millennium Simulation, Illustris TNG, and the Eagle Project, follow the gravitational evolution of hundreds of millions of dark matter particles simultaneously, along with the complex physics of ordinary matter, gas cooling, star formation, supernova feedback, black hole growth. When dark matter is included in the simulations, the results are extraordinary. The simulated universe looks like the real one. Filaments of dark matter form first, threading through space in a cosmic web. At the intersections of filaments, dark matter clusters into halos. Ordinary matter, gas, falls into these halos under gravity, cools, condenses, and forms stars. Galaxies form at the centers of dark matter halos. Their properties, sizes, masses, rotation speeds, the distribution of stars, match the galaxies we observe with remarkable fidelity. The large-scale structure of the simulated universe, the cosmic web of filaments, clusters, and voids, matches the large-scale structure revealed by galaxy surveys, like the Sloan Digital Sky Survey, with extraordinary precision. Remove dark matter from the simulations. Run them with only ordinary matter. The universe that results looks nothing like the one we live in. Galaxies form too slowly, too few of them, in the wrong places, with the wrong properties. The cosmic web is absent. The large-scale structure is wrong. Dark matter is not just an add-on to make rotation curves work. It is a fundamental ingredient of the recipe for building the universe we see. Without it, the universe as we know it, with its galaxies and stars and planets and us, does not form. Dark matter did not just shape the universe, it made the universe possible. And here is perhaps the strangest part of that realization. The dark matter halos that surround galaxies like our own Milky Way are not static. They are dynamic. They interact. They merge. When two galaxies collide, as the Milky Way and Andromeda will collide in approximately 4.5 billion years, their dark matter halos interact first, long before the visible galaxies meet. The dark matter choreographs the collision. It determines the outcome. It shapes the merged galaxy that forms from the wreckage. We are passengers in a dance choreographed by something we cannot see. One candidate for dark matter that has received renewed attention in recent years is not a new particle at all. It is black holes, not the stellar mass black holes formed from dying stars, and not the supermassive black holes at the centers of galaxies. Something different, primordial black holes. In the extreme conditions of the very early universe, in the first fractions of a second after the Big Bang, density fluctuations could have been so extreme that regions of space collapsed directly into black holes before any stars formed. These primordial black holes would not be made of exotic new particles. They would be made of ordinary matter, compressed to such extreme density that they became black holes. But they would behave like dark matter. They would interact gravitationally. They would not emit light. They would form halos around galaxies. They would contribute to the large-scale structure of the universe. Could primordial black holes account for all of dark matter? The constraints are tight. Observations of the cosmic microwave background, gravitational microlensing surveys, and the distribution of gravitational wave detections from merging black holes all constrain the mass and abundance of primordial black holes. The current evidence suggests that primordial black holes could account for some dark matter, perhaps a few %, but probably not all of it, unless they exist in a specific mass range that current observations cannot yet probe. A window of masses, around 1 to 100 solar masses, where the constraints are weaker and primordial, black holes remain a viable candidate for a significant fraction of dark matter. The LIGO and Virgo gravitational wave detectors have detected dozens of merging black holes in this mass range. Some of these mergers have properties, mass ratios, spin distributions, that are difficult to explain by stellar evolution alone. Could some of them be primordial? We don't know. It is one of the most actively debated questions in astrophysics right now. If dark matter halos surround galaxies, then the densest concentration of dark matter should be at the centers of galaxies, the innermost regions where the halo is most compact and most gravitationally concentrated. This prediction leads to one of the most interesting unsolved problems in dark matter physics: the cusp core problem. Standard dark matter simulations predict that the density of dark matter should rise steeply towards the center of a galaxy, forming a sharp central peak called a cusp. The closer you get to the center, the more dark matter there should be, with the density rising sharply as you approach the nucleus. But observations of real galaxies, particularly dwarf galaxies, the smallest and most dark matter-dominated galaxies in the universe, often show something different. The dark matter density in their centers appears to be roughly constant, a flat central region called a core, rather than the steep central cusp the simulations predict. This discrepancy, the cusp core problem, is one of the most actively discussed challenges to the standard dark matter picture. Several solutions have been proposed. One is that the feedback from star formation, supernovae explosions, stellar winds, can push gas in and out of the galactic center, creating gravitational fluctuations that heat the dark matter and transform a cusp into a core. This is called baryonic feedback, and increasingly sophisticated simulations suggest it can indeed flatten dark matter cusps in the right circumstances. Another possibility is that dark matter itself is not perfectly cold and collisionless. Perhaps dark matter particles interact with each other, not through electromagnetism, which would make them visible, but through some new dark force, felt only in the dark sector. This is called self-interacting dark matter, or SIDM. Self-interacting dark matter particles would collide with each other near the dense centers of galaxies, transferring energy and heat, smoothing out the central cusp into a core. The outer halo, less dense, would be largely unaffected. Self-interacting dark matter could solve the cusp core problem. It could also potentially explain some other small-scale anomalies in the dark matter picture. And it would imply that the dark sector, the invisible 27% of the universe, is not a simple collection of non-interacting particles, but a rich, complex world with its own forces and interactions. A dark physics, invisible to us, governing the behavior of the majority of the universe's matter. The idea is both strange and compelling, and it cannot yet be ruled out. If dark matter particles exist and occasionally interact with ordinary matter, even incredibly rarely, they should leave a detectable signal in a sufficiently sensitive detector. This is the logic behind the direct detection experiments, some of the most sophisticated and ambitious scientific instruments ever built. The most sensitive current experiment is Lux Zeppelin, or LZ, located nearly a mile underground in the Sanford Underground Research Facility in the Black Hills of South Dakota. The same mine that once produced gold. Now it produces science. At the heart of LZ is a tank containing 10 tons of liquid xenon, a heavy inert element whose atoms provide large targets for dark matter particles to hit. The entire apparatus is surrounded by layers of shielding, water tanks, polyethylene, lead, designed to block every source of background radiation that might mimic a dark matter signal. The xenon is cooled to -108 degrees Celsius. Every surface is cleaned with extraordinary care to eliminate radioactive contamination. The detector is sensitive enough to see individual photons, individual particles of light, produced when a xenon atom recoils from a collision. When a dark matter particle hits a xenon nucleus, if it ever does, it would produce a distinctive pattern of light and electric charge that the detector can identify and record. The result after years of operation? No confirmed detections. Not one. But no detection is not the same as no progress. Each null result tells us something. It rules out dark matter particles above a certain interaction strength. It constrains the parameter space. It tells us where dark matter is not hiding. And it motivates the next generation of detectors. Larger, cleaner, more sensitive, probing interaction strengths that would have been unimaginable a decade ago. Similar experiments run around the world. Xenon 1T and its successor Xenon NT in the Gran Sasso laboratory beneath the Italian, Apennines, Pandax in the China Jinping Underground Laboratory deep beneath a mountain in Sichuan province. All of them listening, all of them waiting, all of them so far hearing silence. The silence is not discouraging to the physicists running these experiments. It is information. Every year of null results is a year of ruling things out, of narrowing the possibilities, of closing in on whatever the answer actually is. Science is patient in a way that headlines are not. The search for dark matter is not confined to underground detectors waiting patiently for a particle to stumble into them. At CERN, on the border between Switzerland and France, the most powerful particle accelerator ever built has been smashing protons together at energies approaching the speed of light, searching for new particles that might explain dark matter. The Large Hadron Collider, the LHC, accelerates protons around a circular tunnel 27 kilometers in circumference and collides them at energies of up to 13 trillion electron volts. The collisions recreate conditions that existed in the universe a fraction of a second after the Big Bang. And in those conditions, if dark matter particles exist with masses in the range the LHC can reach, they should be produced. The strategy for detecting dark matter at the LHC is indirect. Dark matter particles, by definition, do not interact with the detectors. They escape invisibly, but they carry away energy and momentum that can be measured by the missing energy technique. In a proton-proton collision, the total energy and momentum must be conserved. If you add up all the particles that the detector sees and find that energy is missing, that momentum is unaccounted for, then something invisible must have carried it away. Something like a dark matter particle. The LHC has run for over a decade. Its detectors, Atlas and CMS, each the size of a cathedral, have analyzed trillions of collisions. They have found the Higgs boson. Discovered in 2012, the Higgs was a triumph of the Standard Model, a confirmation of a particle predicted 50 years earlier. They have not found dark matter. Every search for supersymmetric particles, the leading theoretical framework that would naturally produce WIMP dark matter, has come up empty. The supersymmetric particles, if they exist, are heavier than the LHC can produce, or they interact differently than expected, or they simply are not there. The null results at the LHC, combined with the null results in the underground detectors, have significantly constrained the most popular WIMP models, not ruled them out entirely, but pushed them to corners of parameter space that are less theoretically motivated, less elegant, less natural. Some physicists have begun to seriously consider that the WIMP may not be the answer. That dark matter, whatever it is, may not interact with ordinary matter in any way that current or near-future experiments can detect. That is not a comfortable conclusion, but it is where the data is pointing. And in science, the data always wins. Here is a question that physicists are beginning to take seriously. What if we never directly detect dark matter? Not because it doesn't exist, the gravitational evidence is overwhelming, but because whatever dark matter is, it may interact with ordinary matter so weakly that no detector we can build will ever see it. There are dark matter candidates, called sterile neutrinos or certain axion variants, whose interaction with ordinary matter is so feeble that detecting them directly may be genuinely beyond the reach of any technology our civilization could build. If that is the case, then dark matter may be forever known only by its gravitational influence. Forever invisible not because we haven't built the right detector yet, but because the laws of physics do not permit the interaction needed to detect it directly. We would know it is there. The galaxies tell us. The cosmic web tells us. The CMB tells us. But we would never touch it. Never hold a dark matter particle in a detector. Never watch it interact with anything we understand. It would be like trying to see a window by looking through it, the evidence of its presence everywhere, the object itself forever transparent. This possibility is, in a sense, the most philosophically interesting outcome of the dark matter search, because it would mean that the universe is not fully knowable through direct observation, that there are aspects of physical reality that we can infer, can map, can model, can understand gravitationally, but can never directly probe. That the universe has secrets it keeps, not by hiding them in distant places or at extreme energies, but by simply refusing to interact with the instruments we build. There is something both humbling and profound about that possibility. A universe that is 95% beyond our direct reach, that is shaped, structured, and governed by things we cannot see. That has been building galaxies and cosmic webs and the conditions for stars and planets and life, all of it resting on a foundation of something we cannot name. Here is perhaps the most mind-bending possibility in all of dark matter physics. What if dark matter is not just one particle? What if, just as ordinary matter is not just one thing, protons, neutrons, electrons, photons, neutrinos, quarks, gluons, dark matter is a whole sector of particles? A dark sector with its own forces, its own interactions, its own complexity. What if in the invisible 27% of the universe there are dark atoms, dark matter equivalents of protons and electrons bound together by a dark electromagnetic force? Dark molecules, dark chemistry, dark complexity. What if the dark sector is as rich as the ordinary sector? A whole hidden world, parallel to ours, governed by its own physics, interacting with our world only through gravity. This is not mainstream physics. It is speculative. But it is taken seriously by a number of theoretical physicists, precisely because there is no theoretical reason why the dark sector should be simple. We assumed it was simple because simplicity is attractive and because simple models are easier to test. But the universe has no obligation to be simple. The ordinary sector, 5% of the universe, has a rich, complex particle physics. 17 known particles in the Standard Model, interacting through 4 forces, producing an extraordinary diversity of structures from quarks to atoms to molecules to cells to brains. Why should the dark sector, 27% of the universe, 5 times more common, be a single boring particle with no interactions? If the dark sector is complex, if it has its own forces and structures, then dark matter halos around galaxies might not be smooth, uniform distributions of non-interacting particles. They might have structure, dark filaments within the halo, dark clumps, perhaps even dark disks, concentrations of dark matter in the plane of the galaxy, formed by dark matter that can cool and condense the way ordinary matter does when it forms a galaxy's disk. And if dark matter can form structures, dark clumps, dark disks, those structures could have gravitational effects on ordinary matter, effects that might, with sufficiently precise measurement, be detectable. There is even, at the most speculative extreme, the possibility of dark stars, compact objects made entirely of dark matter, invisible but gravitationally significant, drifting through the halos of galaxies. We have no evidence for any of this. It is possibility, not observation. But it is the kind of possibility that keeps physicists lying awake at night, excited, not anxious. Because if the dark sector is rich and complex, the universe is far stranger and far more interesting than even our most ambitious models have suggested. And strange is, in physics, almost always a good sign. Look at that galaxy. 100 billion stars, rotating, held together. What holds it? Not the stars themselves. There are not enough of them. Not the gas between them. Not enough of that either. Something else. Something vast and invisible, surrounding the galaxy like a halo, providing 5 times more gravity than everything you can see. Something we have never touched, never directly detected, never held in a laboratory or watched interact with a single atom of ordinary matter in any experiment. And yet it is there. We know it is there the way you know the wind is blowing by watching the trees move. We see its effects everywhere, in the rotation of galaxies, in the bending of light, in the large-scale structure of the cosmic web, in the ancient fluctuations of the cosmic microwave background. The universe is not made mostly of the things we understand. it is made mostly of mystery. And that mystery is not a failure of science. It is science doing what science does, looking carefully at the universe, measuring what is there, and having the honesty to say, "We don't understand this yet." Vera Rubin spent her career measuring galaxies that didn't behave the way they should. She didn't dismiss the anomaly. She didn't pretend it wasn't there. She followed the data carefully, precisely, patiently, to a conclusion that changed our picture of the universe forever. We don't know what dark matter is. We know it is there. We know how much of it there is. We know how it behaves, gravitationally, cosmologically, structurally. We know what it is not. We know where to look for it, even if we haven't found it yet. And somewhere, in a laboratory buried deep in a mountain, in a telescope mapped to the ancient light of the Big Bang, in the equations of a physicist who hasn't been born yet, the answer is waiting. The universe has hidden its majority from us, but it has left fingerprints everywhere, and we are learning to read them.